So before I go to a specific example, let me just tell you why the convergence gets better. Why do you care about that? So the idea of computing zeros of function like that, or Fredholm determinant, is that I can plot here the value of this function, 1 over zeta. I can vary my parameter s. And what I expect is that, for example, when s is 0, this weight is just 1. And as I change this, my parameter, this function does something and goes to some zeros. And this is what I'm trying to compute. So this will be called S0, the most important one. S1 will have to do with correlation. S2, and they could be real or complex pairs, but I'm pretending they're real just because I can draw it this way on the blackboard. Suppose I show that I can write my determinant as product of 3 determinants. Then what will happen is determinant 1, there'll be 1 over zeta for representation, which we call, let's say, A1, fully symmetric representation. There'll be 1 over zeta for fully anti-symmetric representation. So I'm just using a specific example of the dihedral group D3, or 3-disk example. And then there will be zeta, which is computed on E. Now, in this formula, the 2-dimensional representation appears as a square. So its zeros would look like that. See, this 0 that came from taking determinant of 1 minus operator on the 2-dimensional space squared. But each one of them might be just quite nice. Separately, this one might look like that. That one might look like that. And that one might look like that. And what they have is, they have zeros in different positions. And it turns out the leading 0 will be here. That'll be, a 0 will belong to the fully symmetric representation. Now these are 3 functions. And I multiply them, and I square the last one. So what does that mean? That means that if I'm stupid, which we are 95% of the time, because doing smart times takes lots of time, and I look at determinant of my original system ignoring symmetries, which is product of these 3 graphs, determinant on A1, determinant on A2, determinant, well, I wrote it right here, that's convenient, times this one. Then this function, we have all the zeros these guys have. So I have lots of zeros. Because for every 0 I have here, that's a 0 of the product and square, etc. But the function itself will look pretty crazy because it has to be product of these other guys, and they are uncorrelated. So it has to go through lots of zeros. So if I'm computing this as some kind of expansion and longer cycles, that's sort of a Taylor expansion. So to compute this one, I need a quadratic term, and to compute this one, I need a quadratic term. But when I look at the product function, I'll need a much higher order polynomial to compute the zeros with the same kind of order. So what you'll find in practice is that if you don't use symmetry, try to find zeros, you'll get some result. But it's very much affected by the fact there are lots of other zeros you have to go through. So to get an accuracy even for a leading 0 is much harder than in an invariant subspace. You might nod your heads, but go ahead and do it.
You will not be able to stay home, brother. You will not be able to plug in, turn on, and cop out. You will not be able to lose yourself on Skag and skip out for beer during commercials because the revolution will not be televised.